This is PrachiGupta. Welcome to the next series of the recorded collabs. Before starting, let's just go through what we have covered till now. We have covered from collab 1 to 3, we have covered till collab 14. We have completed all the 14 collabs go through. We have uploaded separate 14 recordings as well as the executed code on the GitHub. Uh, but the next collab that come in our list is introduction to NumPy collab, which we have already covered here. So this is the same collab. So we can skip. We are skipping this collab. It's total same. Nothing, no difference. The same collab is repeated here, and the same goes to collab 16. The collab 16 is already covered. The collab 16 here is introduction to jacks, that which we have already covered here in the collab 4. So if we want to go through this collab 15 16, it's total same as collab number 1 and 4. So we are skipping collab 15 and 16, and now we are jumping to the collab 17, that is advanced checks, which is the last collab. So let's move ahead. So let's start with our advanced Jax. So, welcome to this high performance world of Jax. Jax is essentially NumPy on accelerators with automatic differentiation and XLA compilations. So, it is a framework of choice of cutting edge research as at places like DeepMind and Google Brain. So, let's see how we can use it. First, we are setting up comparisons. So here you can see comparison summary of NumPy, PyTorch, Jex primitive, and Flex. How they are different and why Jex best practices where you can use it. We are doing that. Now let's start with the coding part. So first, we will run the setup shell. We are importing Jex NumPy, and then we are importing the Jex grid, JIT, VMap, everything. Notice PRNG key, like unlikely like NumPy's global random state. Jex uses the PRNG key. This explicit uses it explicit and functional random generator to ensure the reproducibility and purity. So that's what the Rex uses. So we are importing it, and we are defining helper functions like binary cross entropy. We have defined flexible MLP function. We are defining create train state function, and the train step function, and then we are going to do the demo of moon classification. So here we are defining make moons function where we are doing this random PRNG key. So that's what we were talking about. Unlike NumPy's global random state, Jex uses explicit function random number generator to ensure the reproducibility and the purity. So here we are defining the moon 1 theta 1 and the moon 2 theta 2. Once that is done, we will concatenate. We will do JNP concatenate, and we will see return the results. And then we will split the data into training and testing, and then we will call the flexible MLP model, and then we will go to the training state, and then we will train it. We have the epochs and the validation loss defined here. We are calculating the validation logistic, validation prediction, and then validation loss, and storing it in the history. So for each epoch, we are calling training and validation, and we are storing it. We are storing the accuracies, and then we will plot a graph, and we'll see how it actually works. So now we are doing the epochs. We are training the data. We can see uh, the moon data set is very clearly differentiate. It's all separated. So now let's demo XOR with flags. So Next we tackle the XOR problem using flex. This demonstrates how the small network with a 10H activation can learn the non-linear XOR logic, achieving near perfect predictions. So let's see. We have two X and Y, we have this model, we have this training key. We will do the epochs and then we will apply the sigmoid function here and then I'll run it. So here we are training step with the flex and we are applying the sigmoid function, we are applying the logistics. You can see the output. It's very good. With few epochs only we could see nearly to zero loss, and we can see we even got prediction one exact prediction also. So the results look pretty good. Now, this cell formalizes complete flex training pipeline. It defines the models and the state and explaining that the train state neatly bundles the parameter and how forward pass and the optimizer it is neatly bundled. Let's see. So we have defined this flexible MLP. We can see the sequence and the activation. We are defining this call and the activation function, and then we have this dense layer. We are creating a training state. We have defined this train step flex, uh, and then we will run it. So this is the class we have defined. Now the next is we'll dive into the optex. This is a JAX library for optimizer. It shows the standard pattern, initialize the optimizer, update the state with gradient and apply those updates to your parameters. So let's see how it does it. We have this demo. We are printing the names and we are just printing. So let's see. Available optimizers in optex are this. These are the optimizers available and this is its pattern. It will optimize opt state, grades, update and then params. This is the pattern it follows. So this now we will deep dive into a basic flex line and module. We will see how nn.compact allows us to define the layers and their use in a single function, and how model.init creates the initial parameter pi tree. So let's see. So we have defined this simple MLP class where we have this hidden size and output. We will define call function and here we will define the dense and the ReLU. Uh, we will create a model instance and then we will initialize the parameters. We'll call model.init to create the parameters, and then we will use jsx.tree.map to map it. So this create initial parameter of pi tree, and let's run it and see. So this is the parameter structure that we can see, and this is the input and the output. So this is how flex line and basic module we have created. Now once this is done, we'll see the transitioning from low level primitives to production ready flex line and APIs. How can we do that? So we'll see. We will So now in this cell we will revisit our XOR problem, but this time using JX primitives instead of flex. This shows the underhood manual handling parameters, and we can see the XOR and YOR, and then we are dependencies from other cell. We are defining the MLP parameters. We are defining the MLP forward function for the activations, and here we are providing activation functions and using it. Here we are doing the train NLP. We are using JEX for sigmoid and JEX tree dot map. All we are doing all this using JEX, and then we are using history to store the history. We'll run for the epochs and then we will enter dependencies. Once this is done, we will initialize the key. We will call the MLP parameters and we will train the parameters and the history, and then we will test it. And once we test it using JAX, and then we will print the output. We'll plot the graph. So let's see. So this is the output. We create 281 network and then activation using 10H, and we use the binary cross entropy for the loss. We have 10 epoch session for training, and then we had this input, and this was our graph for the loss function. Now, once we this is done, here we will define the functional training loop. Notice the pure function here. Uh, so the pure function pattern parameter goes in and update the parameters, and the updated parameters come out. We use jsx.tree.map to update all the parameter at once. So we will create a training step. We will define the training step here. We'll update the parameter and we will return the new parameters. So this is what we were talking about. One parameter pattern parameter goes in the pattern the parameter goes in and the new updated parameters comes out. Also we will use train mlp. We will use it for the training, and then we will define the mlp forward. Here we will use json sigmoid for the loss type, and then um, we will do the training step here. We will use the history to store the history. We will run the epochs here, and then we will return the parameters and history. So we will run it, and this is the function defined, and this is our key pattern. Once this is done, we'll move ahead with the neural network from scratch, using jax primitives only. So this is the core of building a neural network from scratch. We manually initialize parameter with he initialization and define manual pass. So I'll just quickly run it and we'll see. It is also showing the same thing. Just give me. I have here and I have to. Okay. Yeah. So this is how a network architecture is created with three layers. We have the test input, and we have the output shape, and then we have the output. So this is how our neural network is created from scratch. Uh, we'll move ahead to the loss functions using jax primitive style. So this cell defines common loss functions, MSE, BCE, and the activation functions using only jax primitive. So we are defining mean loss, binary cross entropy, categorical cross entropy. We have defined the test, and we will just run it. We'll just simply testing a simple array with all these loss functions. We also have this activation functions defined using JNP, um, JAX. So define sigmoid, define tanh, define ReLU, define Reiki ReLU, and softmax. All these things we are defining here. The next is neural network from scratch, the JAX primitive. So the pure function for neural network, we have it here. Um, So the JAX requires a functional programming style with no mutable states. That's what we are trying to claim here. Um, Moving towards the gradient descent in action. This cell shows gradient descent in action for a simple mathematical function. F of x is equals to x minus 3 to the whole square plus 1. Visualizing how grad helps us to find the minimum. So let's see how grad helps us to find the minimum. We are plotting the graph. So we'll run it, and we can see we are getting the gradient descent loops, and then we have the starting finalizing points. Moving towards the next part, we have the JAX fundamentals setup. Um, just once this is done, we have here gradients with pi trees in the nested tree structure. Values and grades to get both at once, and then the grade basic differentiation we have done here. Once this is done, we will move towards the JAX core power, that is uh, we'll see basically from NumPy to JAX a complete deep learning journey. Master JAX of principle of production ready code. So what is JAX, why JAX, the JAX fundamentals, everything we are going to see in the upcoming section. So how to import and set up all these things I have already covered now from here in the fourth collab, introduction to JAX tensor. So there you can see how to do setup and import. So I won't explain it here. I'll just quickly move forward. So we were where we were, let me just, yeah, setup and the import, we were here. So all this setup and imports we are doing, I'll just quickly run it. Array fundamentals, it's the same fundamentals that we have seen in starting. Creating array, the data type, the zeros, special arrays, all these things we have already covered in our collapse 4. The functions, all these things we have already covered. PRNG key, the data types we have already seen. Device management, we can see the devices present, we can switch between the devices. The element optimize operation, matrix operation, reduction operation, all these things we have already covered in collab 4. Immutability, we have already seen how it is immutable and how we can't change it, so this also we have already seen. JIT, just in the time compilation, this is also one of the part of the uh, JAX features. VMAP is automatic vectorization, that VMAP automatically adds a batch dimension, example function that works on a single vector. So basically we have defined a function, we will work on a single vector and then we will create a batch, and then we will manually loop the array, and then VMP automatic vectorization, we will pass this single vector to VMAP, and it will automatically add a batch dimension to it. Let's run this and see for the result. We have this single vector function, and the batch sep is 3 3. So manual loop results to 14, 77 and 97, and when we do it with the VMAP, it gives the same result. So this is how VMAP is used. We'll see advanced VMAP uses. So to see the advanced VMAP uses, this allows us to write the function for a single data point and automatically apply it to entire batch without manual loops. So this is one of the advanced use of the VMAP. Now coming toward the composite function, this cell shows the magic of compositions. We combine JIT, VMAP and the grid. We combine all three to compute fast per example gradient, a task that is very difficult in other frameworks. So we will combine all these functions, grad, VMAP, JIT, to perform the faster task. That's what we are doing here. So this is what we are doing. Once that is done, we will see the Einstein summation. This cell demonstrates how the Einstein can perform everything simple transpose to complex attention mechanism used in the transformers. We have already seen this Einstein fundamentals already in the C4, so I'm just moving ahead with Einstein cheat sheet. And yeah, that's all for now. We are done with the JAX neural networks. Um, that's all for today. Thank you, everyone.